speaker today is Yuansi Chen, and he's going to talk about localization schemes. So take it away.
Thank you, John. Yeah, hi everyone. Yeah, I would like to thank organizers for setting this wonderful workshop. And I really enjoy the talks. And today I'm going to talk about localization schemes. This is joint work with Ron and Eldan. So I'm going to, in this talk, I'm going to in this talk, I'm going to show you three localization schemes, and the motivation is to understand the mixing time analysis of Glauber dynamics for different kind of target distributions. And the motivation for me, at least for me, to start this this work is this. It might be like very natural for many of you to say that to understand the mixing time of Glauber dynamics, you have to understand this high-dimensional expanders. And for people from CS background, I'm actually more from statistical probability background. And for me, it's actually more natural to say that, to understand the mixing time of a sampling algorithm, it's enough to understand how some kind of stochastic process works, and we're trying to get in from this angle and say that yeah, it is in many of these sampling problems, it is sufficient to have a good understanding of some stochastic process, and you have a good understanding of the mixing time. So let's set up the problem. We have a target measure. So on the state space, either the Boolean hypercube or R to the n, so n-dimensional space, and we want to draw a sample coming from this target measure mu. And usually you cannot just sample directly. You have to design a Markov chain to sample this iteratively. And one of the Markov chain that works very well in the Boolean cube is the Glauber dynamics. I think this has been explained in, for example, in the bootcamp in quickly Liu's talk about log concave polynomials as spectral independence. So I'm just quickly go through this. And Glauber dynamics is kind of iterative algorithm. Or at each state, it will move to its neighbor by flipping i's coordinate ei with probability with probability 1/n. You choose the index and flip that index, and then you move to that coordinate. You move to a new point y with some probability that you calculate using your target measure, so that you ensure that your stationary measure of your Markov chain is the correct target measure mu here. And we'll denote this transition kernel that describes the probability going from state x to y is this px to y, and this will be a transition kernel of size 2 to the n times 2 to the n. You can think about this like a matrix 2 to the n times 2 to the n. And we want to understand the properties of this transition kernel for some target measure. And so the mixing time analysis, we try to understand, like, given some initial measure, and then you let this transition kernel apply it for k times, and you get a measure at time t, at time k, and you get this measure, and you want to understand how large this k needs to be so that your measure at time k is close to the target measure in some total variational distance. Okay, and so there are many ways to prove the mixing time of a sampling algorithm or Markov chain. One dominant way is actually to prove mixing time by a functional analysis. So I think in the bootcamp we have seen this. We can define this called a Dirichlet form. So Dirichlet form takes in two test functions, f and g, and then compute the inner product between I minus b times f and g with respect to the measure mu. Okay. So if you can prove a Poisson type of inequality for your Markov chain, also called the spectral gap, meaning that if you can prove that for any test function f, the variance on the measure mu times coefficient lambda is upper bounded by this Dirichlet form, then you can show actually this Markov chain has a variance decay, and so this reversible means that the Markov chain satisfies detailed balance condition will have converged to the correct target distribution. Lazy, I just added so that its analysis is kind of easier to show. And Under this condition, you will be able to show that your Markov chain will have some kind of variance decay. So apply one step of your Markov chain. The variance actually is decaying at a rate 1 minus lambda. So then you apply this Markov chain k times, then the variance decays at 1 minus lambda to the power k. So you can change this variance decay and get some kind of bound on the KO divergence between the measure at the iteration k and the target measure, and that will lead you to some mixing time of this form. That will depend on the 1 over lambda. Lambda is the Poisson constant here, and then the log on the minimum value of the initial measure, 1 over minimum value of the initial measure, and the log 1 over epsilon. Epsilon is the target epsilon total variational distance you want to achieve. So this we have seen. So you can have similar functional inequality for the entropy. You can define this modified log Sobolev inequality and define this modified log Sobolev constant by replacing variance with entropy and by replacing the derivative form ff with the derivative form f log f. And then using this modified log Sobolev inequality, we'll be able to prove some KO divergence decay. And the mixing time will depend 1 over this modified log Sobolev constant. And then the improvement is the log dependency on the initialization, because instead of variance decay, instead of like chi-square divergence decay, you get KO divergence decay, and you gain a kind of extra log there. Okay, so so now from now on, we'll focus on like this proving this kind of functional inequalities. So the problem to understand a mixing time of Markov chain, it is sufficient to prove something like this. But the difficulty is that you have a target measure on the Boolean hypercube. Your transition kernel is of a matrix of size 2 to the n times 2 to the n. It's like very large transition kernel. You can see that to understand this Poisson inequality, if you write out the matrix, it's just trying to understand the second largest eigenvalue of your transition kernel. But the problem is this matrix is like too large, and to get a good analysis of the second largest eigenvalue of P. And for product measure, it's usually easy, and you can understand each coordinate independently. And the main question in this sampling analysis that people ask is like, I'm willing to put some assumptions on my target measure, and what kind of assumptions actually will make it easy to prove this type of Poisson inequality, and what kind of assumptions will make Glauber dynamics mix fast in the Boolean hypercube. Okay, let's take a look at the first type of assumptions that is now very famous. It's called a spectral independence assumption that is introduced by Anari Liu and Obai Skaran in 2020. A target measure on the Boolean hypercube is called eta spectrally independent if this pairwise influence matrix has the operator norm bounded by eta. So this pairwise influence matrix is defined coordinate-wise. At each coordinate, the ij's coordinate is the probability of having xj equals to +1 condition on xi equals +1 minus the probability of xj equals to +1 condition xi equals to -1. So it's kind of analyzing the influence of including the i's coordinate on the probability of the j's coordinate. And you form this matrix and compute its operator norm, and this is spectral independence. And they give a sufficient condition for proving spectral gap. So if you assume that all the conditionals of this measure, condition means that you not only consider this original measure mu, but you ping or you condition some of the coordinates. You condition 1 coordinate, you condition 2 coordinate, you condition 3 coordinates. All those conditional measures are spectral independent. Then you can prove a spectral gap of this form. The spectral gap, the lambda, will be lower bounded by a product of numbers that will depend on the spectral independence constant. And if you take, for example, eta, if eta is 1, then you get some kind of telescopic product, and you you will have a polynomial mixing time out of it. Right? Actually, linear in n here, if eta equals to 1. Okay, so that's the previous framework. One thing they didn't say in the paper, but actually people later realized actually this spectral independence, this pairwise influence matrix looks scary, but actually the pairwise influence matrix condition is just a condition on the covariance. You can actually write in the Boolean, like you just have a Boolean density, and you can actually write this pairwise influence matrix and add identity, and you can have this identity, the covariance of your measure mu is equals to diagonal of your covariance mu plus this pairwise influence matrix plus identity. So assuming that this pairwise influence matrix has a spectral norm bounded by eta is roughly equivalent to assuming that your covariance of the measure is bounded by some 1 plus eta times the diagonal of your covariance of the measure. So intuitively, it makes sense to put assumptions on the covariance, right? So if you have a measure that on the Boolean hypercube, if the covariance is small, means that your measure is very concentrated, and then intuitively it should be easy for Glauber dynamics to traverse this measure as long as it's connected. But the intriguing thing is that it actually needs assumptions of all the conditional measures. Not only the original measure covariance is small, but when you ping all the coordinates, you need the covariance to be small. So if you can, yeah, we have many experts here, and if you ask people around, you might get different answers on why they have to put on these conditions on all the conditionals. And yeah, people might say it's like the idea of trickling down, and the idea is clearly inspired by the high-dimensional expander literature. And it's one of those local to global kind of proof techniques we have seen. And the second question we want to ask is like, what are other kind of more principal ways that you can put assumptions on your target distribution so that it makes it easy to prove a spectral gap. Okay, so now we are going to introduce localization scheme. Our main point is to say that for not all, but many situations, localization schemes give you a unified way to think about what kind of assumptions you need to put on the target measure so that you can easily prove spectral gaps. So a localization scheme is just a map from some measure mu and to some stochastic process. So you want to start the stochastic process from the original measure mu, and then it's the evolution of the measure. And then you want to make sure that for any set A, this mu t of A is going to be a martingale. Martingale means that yeah, if you condition on the path up to time s and take expectation, you will get back the mu s of A. Okay, yeah. So our point is that yeah, if you pick a localization scheme and you study the evolution of the variance along the localization scheme, you put assumptions so that the analysis of the evolution of the variance goes through, and then you will get spectral gap. That looks, yeah, this statement looks quite vague now. Let me give you like a concrete example here first. So the first localization scheme we are going to introduce is this coordinate by coordinate localization scheme. So you will have an original measure defined on the Boolean hypercube. You will draw a uniform random permutation of 1 to n, get you k1 to kn. And you will have one draw from this mu, and you define at time s, time I, mu I is the law of the x condition on xk1, xki. The way to think about it is like this. It's usually I think about this way. So at time 0, you only have your original measure, right? At time 1, you are going to consider the law of x conditioning on the ki's coordinate being fixed. the ki's coordinate is a random, the ki is a random variable that can take value 1, 2, 3, 4, 5 to n, right? So you get many random measures depending on what ki is and what is the value of xki is. So you will get like the mu1 will be here, but you will get a 2n number of measures because you can have to fix the n coordinates, choose one of the coordinates, and then you can choose the xki to be +1 or -1. So you will have 2n random measures. And then from any point here, you can continue this process, and you get mu2. And mu2 again, from mu1 to mu2, you have 2 times the n-1 different measures, random measures generated here, right? So you can think about the stochastic process or the stochastic localization process is a compact way of describing this ensemble of measures that is generated in this way. Okay, does that make sense? Okay, so then the claim is that when you consider the spectral independence paper, and the reason that they put eta spectral independence or all conditionals on mu is that they want to ensure that the variance is conserved, or the variance is conserved approximately along the coordinate by coordinate localization, in the sense that you want to show this type of inequality. So the variance at time i+1 is lower bounded by some constant times the variance of time I. Yeah, let me try to show this, and then you get a sense of like having this kind of compact notation of localization. How does that help? Yeah. So you want to analyze the evolution of the variance, right? So you want to first introduce a test function, and then introduce some the mean of the test function. And then you also introduce the variance of the test function. And the inequality you want to prove is that you want to show that 1 minus eta n minus I expectation of yi is lower bounded by the expectation of yi+1. Right, so the first thing to observe is that this mi is a martingale. Meaning that martingale with respect to the filtration, with respect to the randomness generated by xk1 to xki. So meaning that the expectation of mi+1 given xk1 to xki equals to mi. Second thing to observe, we want to relate these two variants. So it's natural to think about the law of total probability for variance, right? So the second to observe is this: you have this identity that yi equals to mi. So this actually this looks scary because all the k1 to ki, but you actually just need to analyze this thing at the level from I to I plus 1, and then think about this type of the law of total probability. In general, you have this the variance of a random variable z. You can write it as the variance of expectation of z given x plus the expectation of variance of z given x. Right. So this is just a translation. This is just a translation of this by analyzing the randomness in the xk plus 1, ski plus 1, and using the martingale properties, and you get something like this. Okay, so now if we want to relate the expectation of yi to the expectation of yi plus 1, we need to bound this quantity. So this is the key quantity we need to analyze. Again, this quantity looks scary, but you can think about if once you are willing to, but everything happens at going from i's coordinate to time I to I plus 1. If you are willing to condition on x ki plus 1 to some values, then analyzing this quantity is just a kind of like analyzing all the conditional probabilities and then summing them up, right? So I'm going to tell you this. Conditional on x k I plus 1 equals to the j's coordinate. This thing, yeah, the calculation is a little bit tedious. I'm going to just show you the result, but everything should be mechanical. So if you do this calculation, so you can do this calculation by actually like conditioning more on x ki plus 1 equals to plus 1 or equals to minus 1. And then you sum this together up and you will get this formula. And then to go from here to here, you will just sum this up. You will get something like expectation of sum up over the probability of x ki plus 1 equals to j, because the ki plus 1 in the construction of the localization scheme is kind of as long as this ki plus 1 doesn't pick any of those the previous ones, it can pick this j freely. So then this is how this weird 1 over n plus I appears, n minus I appears. So this is the probability of ki picking this probability. And then you go from j not equals to k1 to kn, k1 to ki, and you sum this this thing, sum this one thing. Okay, so when you sum them together, it's natural to put this thing in the kind of matrix or vector form, and you get something like 1 minus nsi expectation of mu I in half x expectation of mu I x. yeah. So actually, this thing, when it gets here, it gets simplified a little bit, and this di is the covariance matrix of mu I. Okay, let me. Now you can see that we want to bound this quantity using one yi, right? So if you can square this thing, then you will get the variance of yi. So what all you need here is the Cauchy-Schwarz type of inequality. To mu I here. And you apply Cauchy-Schwarz inequality. You get the variance of mu I of f coming out from here, and then you have a square of this thing. Square of this thing is you get a copy of the covariance of mu I coming out here as well, and di minus 1/2 of theta. Because I get the covariance mu here, already sum things up. I don't need this mu I here. Okay, so now you can see something that is related to the spectral independence condition, or this variance condition. Right, this variance condition for all the pinning for the ice measure mu I will ensure you to be able to bound this quantity. So the spectral independence condition is just saying that this quantity is 1 plus eta. Okay. Or actually, I assume it to be let's say assume it to be eta. So yeah, eta is the spectral independence condition. Actually, it's I messed up a little bit. So eta will be this will be eta. I assume this will be eta. Eta equals to 1, eta equals to only affect a little bit, but you still get some polynomial. But yeah, anyway, so the eta will be it was defined as the spectral norm of d I minus 1 covariance of mu I is bounded by eta. But let's make it symmetric. So.
So di is the covariance matrix.
Di is the did I? Sorry, di is the diagonal of the covariance matrix. It's the diagonal of the covariance matrix, and you can here you just need the diagonal. This the diagonal inverse times the covariance matrix to be bounded, and this is exactly the spectral independence condition. And once you have this this bond, you have bounded this mi plus 1 minus mi squared terms using some eta times the variance of fi, variance of f, and then you take an expectation on both sides. You get something like expectation of fi is less than eta divided by n minus I expectation of fi after yi plus expectation of yi plus 1. Right, so then you get exactly this 1 minus eta n minus I, expectation of yi. Okay, then how do you have this this type of inequality relating the i's variance and the I plus 1's variance, and how do you get a spectral gap bound? You just take a product of all these inequalities, and you'll get something like the product of I equals to 0 to m minus 2, 1 minus eta I minus 1, expectation of yi, expectation of y0. So the expectation of y0 equals to the variance of mu of f, right? So at time 0, you get the original measure, you get the variance of mu f, and then you do the telescopic kind of product, you get less than expectation of y m minus 1. And let's look at what happens at time n minus 1. At time n minus 1, you have obtained all n minus 1 coordinates. Only one coordinate is free. If only one coordinate is free, you run Glauber dynamics on it. This at time n minus 1 will be exactly equals to the derivative form at this. Actually, you only need to put the expectation of this, and then it's less than the derivative form at the beginning. Yeah. This I didn't show, but you can show that this derivative form in general will, when you apply this stochastic localization, in general will be a super martingale, and then you can relate to the original derivative form. And from here, you get a Poisson inequality. You bound the variance using the derivative form, and the coefficient here is exactly the coefficient that predicts you by the spectral independence. Okay, so my point here is that we didn't use the high-dimensional expander. We didn't use this up-down work. And if you find this proof mechanical after you have fixed this coordinate by coordinate localization, I'm very happy, because my point is that what you actually the most design happens in what kind of localization you decide to apply. Once you choose the localization coordinate by coordinate localization scheme, and you will analyze the evolution of the variance in some way, and you put conditions so that the analysis of the variance goes through, and that's the condition, actually usually the condition you need to prove mixing time of your Markov chain. Okay, so then let's also mention there are actually many conditions that people discover in the literature on what are the conditions you need, sufficient conditions you need to prove mixing time of Glauber dynamics. I mentioned some of them. You have semi-log concavity, you have fractional log concavity, entropy independence. Actually, there are many other conditions that like things like entropy factorization, but I didn't mention. But for example, these three conditions, you can think about these three conditions are the conditions that bounds the covariance of the measure, not only for all conditionals, but also for all tilted measures. And the tilted measures are needed to actually show approximate conservation of entropy. So you analyze the evolution of entropy along the coordinate by coordinate localization, and you will notice that to analyze the evolution of entropy, you not only need the coordinates, but also you need the tilted measures. And those conditions are sufficient conditions to prove a modified log-Sobolev inequality. Okay, so now we want to go beyond this coordinate by coordinate localization, and let's first take a tour beyond the Boolean cube and to Rn, and that's where Eldan's first introduced stochastic localization, and we'll get some inspirations from this stochastic localization. You have seen in Nima's talk that the stochastic localization is a way to transform a measure that is living in an n-dimensional space. The way that a measure transforms is that in each coordinate x, it will have satisfied this stochastic differential equation. But you have many stochastic differential equations. They are slightly coupled in the way that the noise is the same, and then they're coupled through this mean vector, mean of the mu t. And you can think about it as like you at infinite decimal time from t to dt, you basically randomly multiply your measure by some randomly tilted linear function, and the random is in this Brownian motion, and it looks scary like this, but actually you can get an explicit form of the measure at time t. The way to think about this is that you have your original measure mu x. The mu t at time t is just a multiplication of the original measure with some Gaussian measure. The Gaussian measure has variance 1 over t. So at mu t, the measure becomes more and more concentrated. But the location of the Gaussian is random. The location of Gaussian depends on this CT parameter. CT follows some kind of stochastic differential equation, has this randomness here. Right. So the picture we had, that picture still works, but you have many more this picture still works, but you have many more measures from 0 to mu dt to mu dt plus dt, and then you have many more kind of measures, and all of this actually are the original measure times a Gaussian measure, but they get a little bit more concentrated, and the location of those random measures are random. We know the distribution of this explicitly, but each one individual ones actually are random, so you can think about it this way. Okay, let me show you a picture quickly so that if you haven't seen this. You start with some uniform distribution and you apply this localization process, and the measure gets transformed. And you can see that it gets transformed by becoming more and more concentrated. Eventually, it becomes like a concentrated Gaussian at somewhere, but the location of that Gaussian is random. Okay, this stochastic localization technique is used a lot in high-dimensional probability as a proof technique. And in general, this type of proof techniques works like this. You want to show some, you have some high-dimensional measure mu, and you want to show some high-dimensional property of this high-dimensional mu. And it's not easy to show it directly. So what you do is basically transform this measure mu via this stochastic localization. And hopefully that at time t, the measure becomes so concentrated that the Gaussian part is so dominant that it's usually easier to prove the property A for that transformed measure. And then all you need to do is to relate this property A of the transformed measure to the original measure. And this is usually done by analyzing those stochastic differential equations. So yeah, I'm not going to talk about this in detail, but you can take a look at this survey paper by Eldan in the ICM proceeding 2022, that this property A can be a lot of things, can be isoparametric inequality, it's related to the KOS conjecture, and can be the concentration of Lipschitz functions in Gaussian space, can be noise stability, or can be Poisson inequalities. And all these things that people try to use this stochastic localization proofs to prove this property A. Coming back to our problem, focus on sampling. We want to show some functional inequality, Poisson inequality, or modified log sublevel inequality. So this functional inequality is our property A. And the general kind of strategy to design the localization scheme is to say that you want to prove some property A, but once you run the process at some time t, and this property A is kind of easier to prove. This functional inequality is easier to prove. And to make the entire proof work, that we actually, for example, to prove the Poisson inequality, we need to make sure that the approximate conservation of variance, so the variance behaves well along this stochastic process. Okay, so this is the picture we had in our paper. So on the left, you have a Markov chain. You have some initial measure, and you run Markov chain, and you get measures at step k and k plus 1. The functional inequality approach actually reduced the problem to saying that you only need to understand how in each step the variance decays, or like how in each step whether you can prove a Poisson inequality. In other problems, it's not easy to prove this Poisson inequality directly. So we take a detour, and the localization gives you a way to take a detour. Basically, you will transform this measure mu through this localization process. I put the red square here because when you run this localization, for each mu, you will get a process. You get many copies of those, like random copies of this mu t. And hopefully, it's easier to show Poisson inequality or variance decay for those transformed measures. And you show this first for the transformed measures. And then you need to relate this left column with the right column. And this is the analysis of the approximate conservation of variance along the localization scheme. And this part is usually easy part. And usually in this, for those derivative forms, you usually have a super martingale. And then you will be able to prove that this is less than some constant times this, less than constant times this, and less than some constant times this, and take this detour, and you will be able to prove it. Okay. Okay, let's take an example on this Ising model. Ising model is a probability measure defined by a Boolean cube with some quadratic Hamiltonian. So it's proportional to exponential of x transpose jx and h transpose x. J is the interaction matrix, and h is the external field. What we show for the Ising model is that if you know that if you multiply your original measure by some negative like quadratic terms here and some tilted part v transpose x, if you know that the covariance matrix of those of measures of this type are all bounded, then you can provide a modified loss of if constant for Glauber dynamics is in this form. And for Ising model, we just shown if the interaction matrix J is a positive semi-definite matrix with operator norm bounded by one half, you can actually show that by an argument from Bauer, Schmidt, and Dagalier 22, we can actually bound the covariance matrix of this type of density with this. And then you can prove a modified log sublevel inequality that is 1 over n times a constant that only depends on the operator norm of the interaction matrix. Yeah, let's talk about this tightness a little bit. So this condition, you needed this interaction matrix to be less than 1/2 is tight in general. If you consider the Curie-Weiss model, meaning that your interaction matrix is proportional to I transpose or a full like everywhere one matrix. However, there's the open problem that if people consider those Ising models under the Sherrington-Kirkpatrick model, meaning that you take this interaction matrix to be some temperature times the GOE matrix, Gaussian random matrix. This approach only gets you the fast mixing of Glauber dynamics up to beta equals to 1/4. but the conjecture, the phase transition actually happens at beta less than 1. So this is an open problem whether you can show mixing time of Glauber dynamics up to beta equals to 1. There are other algorithms, sampling algorithm that is able to achieve up to beta equals to 1, but for Glauber dynamics, it's still kind of open. You can think about it like our bounded type in general, because we only use the fact that operator norm of J is bounded. But for this SK model, you probably need to use more information than its operator norm is bounded by for those Gaussian random matrices. It has a little bit more randomness in this problem. And we will not be able to take advantage, at least in our current proof. And let's take a look at what happens when we apply Eldan's stochastic localization to this Ising model. So you will take some kind of control, you will take a control matrix CT that is 2 times the interaction matrix. And the effect of running the Eldan stochastic localization process on this measure is multiplying its original measure by some Gaussian part. The Gaussian part, now I choose it to have the quadratic part that is 2 times J over 2, that then it's just this. Linearly, it accumulates at time t, and t times J is the quadratic part. And then you have some random linear part that decides where your measure is concentrated, right? So when you apply this Eldan stochastic localization to Ising model, you will get this type of measure. And the interesting about this type measure, at time t, it is equal to the original Ising model. I don't know, at time 0, it's equal to the original Ising model. At time t, you actually removed all the quadratic, all the interaction parts of your Ising model, and you get back some kind of product distribution. And this is the key observation in applying Eldan stochastic localization here is once you get a product measure at time t equals to 1, it's not hard to show the modified log-Sobolev inequality. And then if you think about that diagram, yeah, so this side is easy. Once you get to time equals to 1, you get a product measure. This side easy, and all you have to do is to show some approximate conservation of variance or approximate conservation of entropy. So, so yeah, this part is scary, but you just take derivative. Actually, you take your entropy of some test function with respect to measure at time t, and you take derivative, and usually we'll have some terms that depend on like some terms on dt and some martingale terms that only depend on the Brownian motion part. And then you want to study the evolution of the entropy. Basically, you want to bound this term that appear in the calculation using the entropy. And turns out that if you can bound the covariance of any tilted measure by some constant matrix AT, then you can bound this. You can relate this thing that appear in the stochastic differential equation with the entropy, and then you get an equation that is only on entropy of mu t, and you will be able to lower bound the entropy. Solving this equation, lower bound the entropy in some way. So you can see that in this case, I highlight this red condition. This red condition is needed in this theorem. And we need this red condition because we want, when we study this evolution of entropy, we want this evolution of entropy. You can have approximate conservation of entropy. And for this to go through, you need to bound something that has some terms that appear in the stochastic differential equation. And you put assumptions for this to go through, basically. Okay, so that's a picture for approximate conservation of entropy. Here you replace the variance quantity with the entropy quantities. Okay, I'll just briefly, I only have like 5 minutes. I'll just briefly talk about the third localization scheme that might be interesting for some of your applications. So the third example we're going to consider is this hardcore model. So this hardcore model is again a measure on the Boolean hypercube, and a configuration sigma has positive value if it's supported on some independent set of a graph, and its density is proportional to lambda, the fugacity parameter, to the size of the independent set. And so in this graph, yeah, you can see that the red ones, I draw all the independent sets here. The interesting thing about this model is that the row of +1 and -1, they are not symmetric. Somehow, yeah, putting vertices to be red has much more influence on its neighbors than putting a vertex to be white, right? So somehow you want to design a stochastic process that, so you want to understand the mixing time of Glauber dynamics for this hardcore model, and somehow you want to design a stochastic process that is not symmetric for +1, -1, take advantage of this not symmetry. And so we're going to introduce this negative fields localization. It's kind of inspired then by fields dynamics in this Chen, Yin, and John 2021 paper. This process transform the measure. You can still think about it's kind of some kind of linear tilt measure at each infinitesimal time from S to S plus ds. It is multiplying your original measure by some random quantity that is linear in X. And instead of having some Brownian motion noise here, you actually replace it with some center the Poisson process. So this minus ds is playing the purpose of centering the process. But this part, you will have some kind of Poisson process. But still, yeah, this part, this equation looks scary, but you actually have a simple interpretation of this process. If you define the set AT is where the coordinates the Poisson process has taken value larger than equal to 1. So the Poisson process has fired, or yeah. This AT is an almost surely non-decreasing process of the subsets. And you can actually write the measure at time t as a combination of a random restriction and the tilts. So this measure that I introduced as a stochastic equation, you can write in this short form that at time t, you will pick some set of AT that you will pin the coordinates to +1, condition on those coordinates +1, and then the measure is tilted towards -1 with this amount of tilt, -t or 1 tilt. Okay, yeah, so this so the thing to observe is that this negative field localization process treats the -1 and +1 differently, right? You will pin some coordinates to 1, but you also tilt the measure to -1 so that you remain a martingale, and you kind of treat the +1s more seriously. And it turns out it's kind of enough to analyze the mixing time of Glauber dynamics for sampling the hardcore model. And I don't have time to show this, but so you need two things to make this framework work, localization scheme framework work. You need like for large time, you need the mixing time analysis is easy, or like it's easy to prove modify log Sobolev inequality. And so it's actually known in this Ebar, Henderson, Mans, and Tentali paper that if you have a very large tilt for this hardcore model, you can prove modify log Sobolev inequality for Glauber dynamics easily. And then the second thing in our analysis, you need to analyze the evolution of the entropy. Yeah, so you will, yeah, the mechanical thing is that you will just write down the entropy and take derivative and see what kind of properties of the hardcore model will allow you to bound the things up here that in the derivative and allow you to prove the evolution of the entropy. Okay, so that's it. I'm not going to show the proof, and you can take a look at our paper. It's I mean, there's still a lot of work. Even though we're trying to make this thing mechanical, but there's still a lot of work trying to take advantage of the property of the hardcore model so that the evolution of the entropy becomes easy to analyze. Okay, to summarize, we introduced this localization schemes as a way to analyze the mixing time of sampling algorithms on Boolean hypercube or in Rn. And we're trying to say that there's this high-level thing of designing a localization scheme, and there's this small mechanical part of proving the evolution of the variance that works well along the stochastic localization process. And usually, we can summarize many of the assumptions that in the literature to this assumption of actually approximate conservation of variance or entropy along the localization process. And some of the results, we can recover some of the results of spectral independence and fractional log concavity. We have this bound for Glauber dynamics for Ising model in a unique regime under any external fields. And we have bounds of Glauber dynamics for mixing of a hardcore model in the tree uniqueness regime. And that's it.
Any questions?
Does this generalize to other sampling algorithms than Glauber dynamics?
Yes, that's a good point. So if you look at that diagram, the diagram doesn't specify which sampling algorithm you use, but you actually need the sampling algorithm to work well for the transformed measure. So as long as you can prove the sampling algorithm works well for the transformed measure, and you will make this diagram work. And this part are usually not very dependent on the sampling algorithm you use. Even though I have to say that to be honest, that we didn't try many other sampling algorithms. Yeah.
So you mentioned this results an Ising model with bounded interactions, with whose spectrum of the spectrum of whose interaction matrix is bounded. So there were some earlier results by Eldan, Kohler, and Zeytouni that got the same variance bound, and later we got the same entropy bound. But those results don't require the covariance. Don't require direct interaction, direct control on the covariance of the intermediate things. So can you comment a little bit on, so you somehow reduce the problem to bounding the covariances, but those results somehow don't need it. Could you comment a little bit on why do you think this is needed?
Yeah, that's a good point. Yeah, so for this particular example of Ising model, somehow you can bound the covariance throughout the process, and we take advantage of that. You're saying, previous work you don't really need. You still need it for the paintings, right? Or
so somehow these works always reduce the interaction matrix to a rank 1 matrix.
Yes.
And then they use known results for the rank 1 thing. But in your case, you want the direct control on the covariance of the intermediate things.
Right. I don't remember exactly. What do you need? You also run a stochastic process so that you can reduce to a rank 1 measure, right?
It's a different stochastic localization process.
You need some kind of rank n-1 stochastic localization process to reduce to that. And that part is without assumption or
that part is without assumption on J.
I have to think about that more carefully, but yeah. Thanks for the question. Yeah.
Any more questions?
Can someone use the coordinate by coordinate localization to show that in spectral independence you don't really need the condition of all marginals, just on most marginals or the large ones?
That's a very good question. Yeah. So somehow, if you look at this process, you would think that maybe you don't need all.
Because you're integrating it on another possibility.
But I don't know. I don't know. Or I don't know. Or maybe do you have any kind of examples where that you only need you only have some part of the covariance bounded. But yeah, it's a very good question. Ideally, you want to also like simplify those are distribution conditions to prove spectral valence bond. But yeah, maybe in some cases you don't need all of the.
Okay, let's take any further questions offline, and let's thank you, Yuansi, again. We'll turn at 2 after lunch.